satellite is a free falling body. Imagine this pen. This pen is a free falling body. So it's the gravity that keeps them going in the particular orbit. A satellite is a free falling body which can never reach the Earth's surface. That's the first thing. What is the exact principle of launching a satellite? So let's say this is an artificial satellite, fixed satellites, and signals can be sent to these satellites and then further processed and sent to other points. Hello students, welcome in today's class. In today's class, we are going to talk about a very important topic of physics, that is satellite. In general also, it is a very interesting topic, so I think you should enjoy today's class. So without wasting any time, I think we shall start. So the first thing that I would tell you about satellite is that satellite is a free falling body. Imagine this pen. This pen is a free falling body. A satellite is also like a free falling body. But then what is the difference? So imagine if I project this pen, I impart it some velocity, then also it is called a free falling body, because the only force acting on this pen is the force of gravity. And that is the case with satellites. Satellites are not governed or driven by any other force but the force of gravity. So it's the gravity that's keeps them going in the particular orbit. But then why does it happen that it does not fall on the Earth? That is the question. Because if you release anything, it will always have a tendency to fall towards the Earth's surface. But then why does not that happen with a satellite? Let's find it out. So put down the heading satellite. Alright, so the first thing is, what is a satellite? It is a free falling body. But then the question arises, why does it not fall on the surface of the Earth? The answer is here. Let's find it out. A satellite is a free falling body which can never reach the Earth's surface. That's the first thing. Next, what is the principle of launching a satellite? So a satellite is provided with an orbital speed in a desired orbit such that the gravitational pull of the Earth is there. There's no doubt about it. The pull is there, but this is used up in providing the necessary centripetal force. So now listen to me very carefully. I do expect that you know the basics of circular motion, because satellite is majorly circular motion around the Earth. Let's say if we are talking about satellites of Earth. Okay. Moon is a natural satellite of the Earth. We do know that we have a natural satellite, and that is in the form of moon. The time period of moon around the Earth is approximately 28 days, 27.3 days, that you also maybe have an idea about. Okay, so that's about satellite. Just the basics, that what is a satellite? Any object that is revolving around another heavy object. Let's say moon is revolving around the Earth, so we will call moon as the satellite of Earth, right? Okay, so let's have a just casual discussion about what are the number of moons for different planets. So Mercury does not have any observable moon. Venus also none. Earth of course one, that's quite heavy, like in the form of moon. Mars has 2 moons, very small, in the form of Phobos and Deimos. Okay, Jupiter has 79 moons because it has a strong gravity, so it must have pulled a lot of asteroids or meteors in its orbit, and that is why it has many moons in the form of 79 moons. That is observable moons that we have observed till yet. Then Saturn has 52 moons, Uranus has 27, and Neptune has 14. So that's about satellites. We are talking about satellites of planets right now, but if you pay attention to this, even Earth is a satellite to the sun in a way, because we are also revolving around the sun. So what can we call satellite as? Maybe a revolving body around another heavy object which is under its influence of gravity, isn't it? So that's what a satellite is. I hope you understand, but the question still exists. Why is then Earth not pulling the moon? Why is the moon not reaching the Earth? If it is still in the field of Earth, it should at the end reach the surface of the Earth. Just like any other object, you throw any other object, gravity will ultimately pull it towards the surface. Then why the moon is not falling on the Earth's surface? Let's find out. Copy down the basic definition, then we move forward. Alright, so now listen to this very carefully. What is the exact principle of launching a satellite? So let's say this is an artificial satellite that we have launched into its desired orbit. How does it function? So what happens is that we first use some rocket arrangement to take the satellite into the desired orbit. Once it reaches there, we ensure that it has some orbital speed. So I'm not saying it is out of the Earth's gravitational field, it is still very much there, but the gravitational pull of the Earth is used up in providing the necessary centripetal force. So what can we write? We can write the gravitational force of the Earth is used up in providing the necessary centripetal force. Now let's write the values. So that's mv square by r. Now what do you mean by all this? So r is called the orbital radius. R is called the orbital radius, right? M is the mass of satellite. I am denoting it by lowercase m, and the mass of the Earth I am denoting by uppercase m. Okay, so I am talking about satellites of Earth, some artificial satellite, let's say, and now this should be gmm over r square without a doubt. So one factor of r and factor of r cancels out, mass cancels out, that is the mass of the satellite cancels out, and this is the orbital speed, that is root gm by r, isn't it? This is root gm by r. Now here we have assumed a very simplistic situation where we have assumed that this satellite is orbiting in circular path. But let me tell you that many natural satellites like moon or our motion around the sun, these are in the form of elliptical paths. So we are open to that this might not be exact circle but can be an ellipse. As you understand, circle is also a special case of ellipse only, right? So we are discussing the simplistic case where we have taken the satellite to be revolving in exact circular orbit. Okay, so now you understand this is the orbital speed, and what factors does depend this orbital speed depend on? M, capital M, that is the mass of the Earth, and the orbit radius, right? And when I say radius, it has to be measured from the center of the Earth. It has to be measured from the center of the Earth. Keep that in mind, because if you talk about this, the radius of the Earth, we denote it by capital R. So if we denote the distance from the surface, let's say we call it h, then you should understand that r is equals to r plus h. I will repeat that again for you. When I say lowercase r, that's the orbital radius, that is the radius of the orbit, taking Earth's center as the center of the orbit. But if you mention the distance from the surface, then this distance, the radius of the Earth, also needs to be added. So if you wish to write this orbital speed in that terms, then you should write it as gm over r plus h, isn't it? That's the orbital speed for you, okay? And it thankfully does not depend on the mass of the satellite. Now why do I say thankfully? So imagine there are multiple satellites in the same orbit, which is very much true. Now we are launching so many satellites every now and then, so there might be multiple satellites in the same orbit. If that is the case, they all thankfully are moving with the same speed in that given orbit, regardless whether they are heavy or light, whether they have more mass or less mass, and there is no chance of collision among the satellites. So that is a good thing, that all the satellites in a given orbit will always be in a in a very synchronous manner, revolving around the Earth without any possibility of collision, right? So that's orbital speed. So now do you understand why Earth's pull is there, but still the satellite is unable to fall on the surface of the Earth, right? So that's about orbital speed. Write it down, then we move forward. Okay, so that's the principle. You do understand that we take the satellite in the desired orbit, then we provide it with that orbital velocity so that it is never able to reach the surface of the Earth. In fact, you can talk about one more thing here, that what if satellite is very close to the Earth? Satellite is close to the Earth. So if that is the case, if the satellite is very close to the Earth, then you know what, we can approximately take R as capital R. So you should know some data. Approximate mass of Earth is like 6 into 10 raised to the power 24 kilograms, and the radius of Earth is approximately 6400 kilometer. So if we put those values, we assume that the satellite is very close to the Earth, then the orbital speed will turn out to be approximately root gm over r, which is going to be approximately 7.9, or let's take it 8 kilometers per second. Okay, so the satellites that are very close to the Earth will be revolving at a speed of 8 kilometer per second around the Earth. So that is how fast they should be moving, so that Earth's pull is still unable to pull them towards the surface and is only able to provide the necessary centripetal force. Okay, what about the time period then? So time period is a very important aspect. Just now I talked about it. For example, moon, more than the orbital radius, we were concerned about the time it takes for the moon to complete one revolution. The orbital radius is approximately 3 lakh, like the distance of the moon from the Earth is approximately 3,85,000 kilometers. That is another thing, but it takes approximately 27-28 days for the moon to revolve around the Earth. So that's what time period is. The time period is the time taken to complete one revolution, which should be distance upon speed. Now, what is the distance of one complete orbit? That's the circumference, that's 2 pi r divided by the speed. So that is going to be 2 pi r over under root of gm by r, and when you do that, this time period turns out to be 2 pi over under root of gm r power 3 by 2. So that's time period for you, time period of any satellite. T square is proportional to r cube. This is also something that you should keep in mind. Why? Because we might want to compare two planets, let's say. So T1 square over T2 square is going to be R1 cube over R2 cube. What does this mean? For example, if we take us as a satellite, the Earth as a satellite, approximately it takes 365 days to revolve around the Sun. So we can estimate the time period of, let's say, Saturn also. How? By using this relation, that T Earth square over T Saturn square is equals to orbital radius of Earth square cube to the orbital radius of Saturn cube. So that is how we can compare time period of different planets. And not only that, we can use this formula for us. Like, we can put the time period as 365 days. We do know the distance between the Earth and the Sun and get the mass of the Sun then. Because if we take us as a satellite, then this becomes the mass of the Sun. So imagine, just by staying at the Earth, we can realize that how heavy the Sun is just by making use of this formula. So how fascinating that is, that it's making our job easy. Otherwise, how could we think of measuring the mass of the Sun? But this formula, you apply this, take this time period as 365 days, take this as the distance between the Sun and the Earth, and this will straight away give you the mass of the Sun, approximately mass of the Sun. So that's about time period and the orbital speeds. So you now understand what orbital speed is. It is the pre-decided speed for a particular orbit in which the satellite should revolve, so that it is unable to reach the surface of the Earth, as the entire force of gravitation gets consumed into providing the necessary centripetal force. Copy this down, then we move forward. Alright, the next thing that we should talk about is certain special kind of satellite, let's say geostationary satellite. Okay, so let's say if I have this arrangement, and let's say there is a satellite like this, Okay, so what do you reckon? Like it is in the same like orbit which is including the equatorial plane. Imagine this as a satellite and imagine the time period of this satellite to be 24 hours. The time period of this satellite to be 24 hours. So it takes 24 hours to complete one revolution while Earth rotates about its axis in 24 hours. Now imagine this. Let's say the Earth is rotating from west to east, right? And the satellite is also rotating in the sense west to east, all right? Now imagine, and it is lying in the equatorial plane. It is lying in the equatorial plane. Now listen to this. Imagine this is the Earth and this is the satellite. It will always be in sync with the rotation of the Earth. So if that happens with respect to the Earth, this satellite will always remain stationary because it is revolving exactly in the same fashion as Earth is rotating. So you know what? It will remain stationary even though it is moving, but it is moving with the Earth, like rotation of the Earth. That is why it will appear stationary. Such satellites are called geostationary satellite, as the name implies. Geostationary. There are other satellites as well, like there can be any other satellite like this or like some other orbit. So there can be multiple, but these satellites are very special because they have a particular position in the sky that helps us to receive signals very easily, as we don't have to readjust the location of the catching device or the dish, and we can always receive signals. So for communication purpose, etc., we can definitely rely on geostationary satellite. There's one more category which is called the geosynchronous satellites. These are also having a time period of 24 hours, all right, but they remain inclined to the Earth. So they don't revolve in the equatorial plane, but they have a different purpose. They have a time period of 24 hours. They remain in a particular orbit like this, but it's not coinciding with the equatorial plane. Okay, so that is also, you know, something that you should know, because you should not get confused. Geostationary and geosynchronous. Okay, so there are two types of satellites. Rest, just as I was telling you, that we can have satellites very close to the Earth, right? Specifically like across the North Pole and the South Pole. So in the polar orbit, okay, such satellites are called polar satellites, okay, which revolve like in this fashion, where the, we can say the radius is approximately equal to the radius of the Earth, as they are, you know, revolving just at a height of 200 or 300 kilometer. So we can say they are very close to the surface of the Earth. And in that case, you should know that I have just talked about it. Orbital speed turns out to be approximately 8 kilometers per second. So they revolve very fast, and their time period is also about 84.6 minutes, or like 1.5 hours or so. So these satellites are also very crucial, as they keep revolving and they can track the cloud movement, and they can help in weather forecasting, or they can also help in, you know, imaging the Earth, as they are lying very close to the surface of the Earth, so they can get better pictures of the Earth. And how? Because, you know, Earth is rotating in the west to east sense, while these satellites are rotating in the polar orbit. So they are able to scan most of the Earth while they are revolving, right? So every satellite has a specific purpose, like precisely we launch them in that particular orbit and in that particular sense to achieve a specific task. But you should be comfortable in this, that what do you mean by a geostationary satellite? What do you mean by, you know, lower orbit polar satellites? Okay, so geostationary satellite, we can write that, you know, the time period is 24 hours, which we may convert in seconds by multiplying it by 3600, and then equate this to the formula of time period, that is 2 pi over under root of gm r power 3 by 2. Now we know the mass of the Earth, and r approximately from here turns out to be 42,000 kilometer. So listen to this very carefully. These geostationary satellite lie at a distance of 42,000 kilometer from the center. So their height is approximately 36,000 kilometer. Their height is approximately, so when I say height, I always mean the distance from the surface, while when I say radius, I always mean the distance from the center. How would they differ? By the radius of the earth, which is approximately 6,000 kilometer. That is why if this is 42,000, this has to be 36,000. All right. So that is about orbital velocity and time period of a satellite, and specifically geostationary satellite. You can copy this down, then we move forward. All right. So I've written everything for you. It is a satellite whose period about the earth is equal to that of the earth about its polar axis. A geostationary satellite is about 35,870 kilometers above the equator. The artificial satellites are broadly classified into two types. Communication satellite, as I just said, that you can have fixed satellites and signals can be sent to these satellites and then further processed and sent to other points. But the good part is that the reception and transmission of signals becomes easy because the satellites are fixed with respect to us. Okay. Remote sensing is like when you are visualizing a particular spot, you can have a geostationary satellite at a particular spot and you can use that to continuously track the progress of that place. Okay, so communication satellites are mainly used for communication. Of course, they link remote areas of earth with telephone and television with a network of geostationary satellites. So we can have an array of geostationary satellites who can communicate with themselves, among themselves, and even with the transmitters and receivers on the earth, and that is how this works, right? And this can be broadcasted all over the world simultaneously. These satellites are also used to take photographs of clouds around the earth, which help in weather forecasting, right? Now, remote sensing satellite, as I was telling you, are also used to estimate the natural resources. They can be very close to the earth's surface as well. They are usually placed in low flying polar orbits. They can take photographs of large areas of land. Hence, they can be used to study resources such as forests, river, mineral deposits, agricultural crops, etc. They are also used for military purpose. So this is just for general knowledge that you should know how and what purposes any satellite would serve. So now you understand what satellites are. Earth only has one natural satellite. All the other satellites are artificially launched by human beings, and how that is done, it's taken to the particular orbit where you want it to revolve and then provided with that appropriate orbital velocity. The closest you get, more the orbital speed, and if you get the closest to the earth, the orbital speed is approximately 8 kilometer per second. Keep that in mind. All right, copy down the important stuff, then we move forward. All right, so the next thing is energy of a satellite. So now when we talk about energy of a satellite, let's quickly do that. Any satellite, let's say this is the earth, any satellite, let's say, is in an orbital radius of r, then it will have a kinetic energy, of course, which is going to be half mv square, and that's going to be gm by r. I hope you understand why, because I've substituted root gm by r and squaring that will give me gm by r. So kinetic energy component is gmm by 2r. That's kinetic energy for you. Now potential energy, as we already have studied about that, it's going to be minus gmm by r, taking infinity as the reference, right? So total energy is going to be kinetic energy plus the potential energy, and that is going to be, like, if we put the value, that's going to be gmm by 2r for kinetic energy, and for potential energy it is going to be minus gmm by r. So the total energy here turns out to be minus gmm by 2r, isn't it? If you add these two terms, what does this indicate? Two things. First, total energy is negative. Keep that in mind. So whenever total energy is negative, we obviously call it as a part of bound system. We call it as a part of bound system. So any satellite that is revolving around the Earth or any satellite revolving around another heavy object is always bound to that. Okay. In fact, if you want it to escape the gravitational field, you need to increase its speed. If you remember, for escaping, I'm just giving you a very like short brief on this, but if you remember, for escaping, we want something to escape, that means its total energy has to become 0. So if that is the case, then we would write kinetic plus potential becoming 0, and kinetic is like half mv square. So we will write it as VE for escaping, and this is for escaping, all right. This is for escaping. So, and potential is like minus gmm by r. So when we equate this value to 0, the escape velocity that we had derived is like root 2 gm by r. Okay, so that's more than the orbital speed. That is why we cannot say that a satellite can escape. If you want it to escape, then you need to increase its speed. By how much? So what is the difference between escape speed and the orbital speed? So that's going to be, can we write this as root 2 times of orbital speed? Of course we can, because orbital speed is root gm by r, escape speed is root 2 gm by r. So this is like root 2 times of that. So can we write this as root 2v minus v? Of course we can. So that's like 0.414, and if we do the fraction, then it's going to be 41.4%. So we need to increase the speed of any satellite with what it has already by 41%, and you would be able to escape it entirely from the gravitational field of the Earth. But right now it's not escaping because it has a total energy in negative. That means to make it 0, you need energy. Just like electrons revolving around the nucleus are a part of bound system. You want to escape them, you need to provide them with energy. In fact, if I talk about electrons, there is a striking similarity which you might have realized after looking at these three energy, this, this and this. So can you see a quick relation? Let me write that. Total energy is negative of kinetic energy. At the same time, it is half of potential energy. Can you realize that? Total energy is this, and this is negative of kinetic energy, but it is half of the potential energy, which is very similar to what electrons' energies were looking like when you talk about them revolving around the nucleus. That is why the Rutherford's model of atom, where he predicted that electrons revolve around the nucleus, was also called the planetary model of atom. So just like planets revolve around the sun, electrons revolve around the nucleus, and the energy relation there in case of electron was exactly the same, that total energy is negative of kinetic energy, is half of the potential energy. So there's a lot to learn. We've learned a lot here. I will wait, you copy down, then we move forward. Okay, next thing is a binary star system. So I wanted to give you a brief here that what is a binary star system. So what happens if there are two stars very close, like not that close but relatively close, you know, suddenly in their gravitational effect, like very close, such that they start impacting each other gravitationally. So what will happen is, if they have a comparable mass, so think about it like that. How did moon come into existence? You know, you can think of it like moon was, let's say, another mass, another rock which came into the gravitational field of the Earth, and Earth in a way, you know, got hold of it and it started revolving around the Earth. That's how you can imagine how moon came into existence. Some people though also say that it might have been a part of the Earth and detached from the Earth after a collision with an asteroid, but we don't know what exactly happened. So that is how it can be, you know, one star can come into the vicinity of another star and then they both start revolving because both are of comparable mass, and then when they revolve around their common center of mass. They start revolving around their common center of mass. So let's say this radius is r1 and this radius is r2. So there are two equations. First, m1 r1 is equals to m2 r2 is the governing equation about their common center of mass. Okay, so this is an optional part. If you don't know about rotation, if you don't know about the concept of center of mass, you can skip this particular part. So, you know, in a way, like, they both are satellites of each other, but they both are revolving. That is what is happening here. Okay, so let's write the equation for the M1. So we will write m omega square r is equals to g m1 m2 over r square. Okay, now what is r? R is the distance between the two, which is r1 plus r2, isn't it? Okay, so this is the first equation and this is the second equation connecting r1 and r2. First, r1 plus r2 is equal to the distance between the two stars, and m1 r1 is equals to m2 r2. So let me surprise you here. You might be seeing a star in the sky, but ultimately, you know, when you use a telescope, you might realize that it is two stars. But because you cannot resolve them, for you they are so close that you see them as one, but ultimately you realize that they are two stars revolving around each other. So that is how it is happening. So m omega square r is equals to g m1 m2 over r square. So when we use equation 1 and equation 2 to get the value of r1 and r2, we will get r1 is equals to m2r over m1 plus m2, and r2 is equals to m1r over m1 plus m2. All right. So let's put this value of r1 in this equation. So this will give me m2r over m1 plus m2, and that is equals to g m1 m2 over r square. m1 cancels out, m2 cancels out. Okay, and what are we left with? We are left with omega. So this was omega square. Okay, let's write it in this fashion. Omega square r cube is equals to g into m1 plus m2, or we can write omega is equals to under root of g m1 plus m2 upon r cube. That is the omega, and the time period will be 2 pi by omega. Now why do I tell you this? You should understand two things about binary star system. Since they are two stars of almost equal mass or comparable mass, they both do not, like, not only one of them revolves, both have to revolve, and both revolve around their common center of mass. Both revolve around their common center of mass. Keep that in mind. Okay, and when both of them revolve around their common center of mass, they both have the same angular speed. Can you realize that? Why do they have the same angular speed? Because when I wrote this equation, ultimately I got a symmetric function. So think of it like that. What if I would have written this equation for m2? Then also I would have written that the gravitational force is providing the necessary centripetal force, right? So in that case I would have written this as m2 omega square, but here we would have had like r2, and when we put the values again, m1 m2 and m1 m2 would have been cancelled out. So that means that, do you know, understand, in spite of them having different radius, you know, the heavier one will be closer to the center of mass and the lighter one will be further away. So they both have different radius, but yet they have the same time period. They have the same time, so they will always be in a sync. So for example, it is the location right now. So this is how they are going to move, and ultimately when this will reach here, this will reach here. So they both will cover the whole revolution in exactly the same time. So that is how, you know, a binary star system works. So just for your general knowledge, you should know two things, that here time period does not depend on the particular radius, right? It only depends on the distance between the stars, but it does not depend on their individual radius about the center of mass. So that's about binary star system, where we are not assuming that one heavy object is fixed and the other one is rotating, or sorry, revolving around that, but rather they are both revolving in this fashion. Okay, so that is how, in a way, like this is working. And now I wish to talk about a little bit about Kepler's laws, not very much in detail, but just to give you a feel of how, you know, planets are satellites to the Sun. Copy this down, then we move forward. Alright, so now let's talk about, the Kepler's law. So Johannes Kepler, 1609, that is part of the 17th century. He came up with these 3 laws. I'll quickly read them for you. First, all planets move around the sun in elliptical orbits, with sun situated at one of the foci. Okay, so that's, you might be understanding what ellipse is and what focus of an ellipse is. Second, a line joining to any planets and the sun sweeps out equal areas in equal intervals of time. So I will talk about it, don't worry. And that is also called the areal velocity. The area swept by the radius vector per unit time is called the areal velocity. Don't worry, in the next slide we are going to talk about it in detail. Right now I'm just taking the names and the definitions of the laws. Third, the square of the period of any planet is proportional to the cube of the semi-major axis. So t square is proportional to a cube, somewhat very similar that we have just realized. Alright, just write down the names and then we move forward. Alright, so look at this in context of Earth very quickly. This is the position where Earth is closest to the sun, that's the perihelion. So what you can realize straight away, that it's an elliptical path with its center here. Maybe this is one of the foci. So here it is closest to the sun. So those people who know about ellipse, they might be knowing what eccentricity is and how you locate the coordinates of the sun, but right now we are not doing that. Okay, so this is the closest distance. That is approximately 147 million kilometer, and like this is the farthest distance, so that's like a little bit more, maybe 152, somewhat like this. Okay, so this is the closest and this is the farthest we can go from the sun. So this position is called perihelion, this position is called aphelion. All right, this position is called perihelion and this position is called aphelion. So these are the two positions where Earth is closest and farthest. So right now I am talking in context of the Earth. The other planets also revolve around the sun in elliptical paths. Okay, now please don't correlate the closest point and the farthest point with the summers and winters, because I hope you understand that summers and winters is very subjective. Throughout the Earth, summers and winters is not at the same time. Maybe June, July, the northern hemisphere we have summers, then the southern hemisphere will have winters, and vice versa in December. So let me surprise you here. Perihelion, when we are closest to the sun, is like approximately 2nd or 3rd January, somewhat like this. So that is when we are closest to the sun. In fact, around about 4th or 5th of July is when we are farthest from the sun, that is aphelion. So then how does it affect the summers and winters? So the summers and winters is caused by this 23-degree tilt of the Earth as compared to its revolution planes, right? So this is like 23-degree tilt. So this approximate tilt, this is the day, understand this, this is the day when the Tropic of Cancer is receiving normal radiation from the sun. So the summers and winters is associated with the fact that whether we are getting perpendicular rays or inclined or slant rays of the sun. So 21st June, very close to 4th of July, is the time when Earth, Tropic of Cancer or region around that is the northern hemisphere, is receiving direct radiation from the sun, hence causing the summers. While this is 22nd December, which you call as the winter solstice, is the time when the Tropic of Capricorn is receiving normal radiation from the sun, hence causing summers in the southern hemisphere. So now you understand how summers and winters work and why planets are not in circular orbit but in elliptical orbits. This is perihelion, this is like aphelion. One more thing, like let's now relate this with Kepler's law. So Kepler's laws is like this: if this is the center, this is the focus, and the semi-major axis is like this is A and this is also A. So now only for those students who have learnt about conic sections, about ellipse, they might be knowing how to define the coordinates of this. So this is called the focus, and the coordinates of this, let's say, is AE comma 0, right? So on the left, then you can call it minus AE. So the closest that we can get, so this whole is A, but this is AE. So this is A minus AE, where E is the eccentricity. So that is equals to A times 1 minus E, while the maximum distance is going to be A plus AE, and that is going to be A1 plus E. So are you able to correlate with the first law now, that all planets move around the sun in elliptical orbits with the sun at one of the foci? Correct. Next, the planets sweep equal areas in equal intervals of time. What does that mean? Let's say you are very close here. Let's say this is R1, and in a very small time dt, you sweep an area dA1, okay? Then you are very far off, and this is, let's say, in dt time, you sweep this area dA2. So what is this law saying? This law is saying that a line joining any planet and the sun sweeps out equal areas in equal intervals of time. What does that mean? So let's say this is the line joining the planet and the sun. So this area dA1, approximately taking it as a triangle or an arc, because it is a very small part. Whenever we talk about velocity, that's instantaneous velocity. So that's going to be half times base times height. So base is going to be V1 into dt, and height is approximately, let's say, R1. So dA1 by dt is going to be half times V1 by V1 times R1, right? That is the aerial velocity. Similarly here, dA2 is going to be half times V2 dt times R2, and dA2 by dt is going to be half V2 R2. Now what does this tell you? When we are revolving around the sun, is the radius same? No, radius is changing. But velocity and radius product, that decides the aerial velocity. What do we call this? Aerial velocity. That is the rate at which the area is being swept, right? That is constant, because that is decided by the product of V and R. And if you know about angular momentum, so this is all optional. If you know about all these things, only then you go into this discussion. So angular momentum is like mvr, is like mvr. So mass of the planet is not changing, so vr is constant, or we can write, let's say, L by m is equals to vr. Hence the aerial velocity, which is vr over 2, becomes L by 2m. So the aerial velocity remains constant. Why? Because the angular momentum remains constant. Why? Because the force is always passing through the sun. So the torque about the sun is 0, and therefore the angular momentum remains conserved and the aerial velocity remains conserved. So can we say that when r is less, that is when we are close to the sun, velocity is more, and when we are far off, where r is more, velocity becomes less. So when we are at the position of perihelion, we are moving at the highest speed, and we are at the position of aphelion, we are moving at the lowest speed, right? So that's Kepler's second law, law of areas, what aerial velocity is. I hope you have got a decent idea if you know the basics of it. If you don't, then you just know the law and don't worry till you actually study about angular momentum and all these things. Okay, so that's about, this general knowledge that you should have, that summers and winters is not related. In fact, I had another diagram to exhibit this, that what if you keep the earth static and study the movement of sun. So that's 21st June for you. That's where the sun is just above the Tropic of Cancer, and you receive normal radiation here in the northern hemisphere. While this is 22nd December, that is the winter solstice, where the Tropic of Capricorn is going to receive the normal radiation, and we will have a situation of summers in the southern hemisphere while winters in the northern hemisphere. But that is where the sun exists, in this zone which you might call tropical zone or the torrid zone. This is where sun exists. Outside that, sun will never be able to give its normal radiation, and you won't have that extreme summer situation, right? So that's about Kepler's laws. I was trying to accommodate all the concepts that you need to know related with satellites, natural, artificial types of satellites, energy of satellites, binary star systems, Kepler's laws, and I hope I was able to accommodate most of the concept within this 45-minute video that I was trying to do, so that you can revise your concepts and this could help you in your exam time. So that's all for this particular video. We'll keep coming up with such videos. Thank you very much for your time. See you in the next one. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.